webcasting it and putting it online. So, okay, microphone's working. All right, Charlie Lindsey. Lindsey is our speaker today. He began his career in solar research in the early 70s under the supervision of Hugh Hudson at the University of California at San Diego. And then in the late 70s to the early 90s, he worked with John Jeffries, Frank Orrell, and Eric Becklin at the University of Hawaii, pioneering solar observations in the far infrared from Mauna Kea and from the Kuiper Airborne Observatory. He also worked with Doug Brown in his development of the modern groundwork for local helioseismology. And in the 90s, Charlie moved to Tucson and worked with Karen and Jack Harvey at the Solar Physics Research Corporation, continuing collaborations with Doug Brown, further developing local helioseismic diagnostics of magnetic regions, including, as somewhat as a spin-off, an acoustic monitor for active regions in the far hemisphere of the Sun. In 2002, Charlie joined the solar group at Northwest Research Associates, which is where he is now. And he's been helping Doug Brown, colleagues in Australia and Germany, and here at ATO, ferment the lathe for some of the nascent fields of this generation, such as flare seismology and magnetohelioseismology. And today he's going to be talking about his work with Alina, what's that name? Alina Donea at Melbourne, Mark Rast at CU LASP, and Bob Steiner at MSU on the quiet sun. So, all yours.
Thank you for that. A very generous introduction, Rebecca.
I got it from you.
Great.
Thank you.
Well, okay then. Let's go. I'm going to talk about something that work that I'm doing. In fact, with Alina Donea, or at least she's the one who kind of started it. And but in the meantime, the number of other people involved are rapidly expanding. Mark Rast, Bob Stein, they ought to be co-authors on this talk, but they haven't seen it yet. So at least for now, this is it. But they really certainly deserve credit for the contribution that they've made to this. So. Okay, well, I want to talk then about something that's fundamental to helioseismology. Helioseismology is what can be thought of as the use of waves that inhabit the solar interior to do diagnostics on the sun, on the structure of the solar interior. You could say to look into the solar interior in a certain respect. And the particular techniques that we're exercising right now are very much the analogy of what electromagnetic optics has given. Now, I like to submit this challenge to people who, are interested, and say that electromagnetic optics, well, no, let's not even stop there. Let's just say optics in general is the most powerful diagnostic utility known to man, by far. True or false? And I challenge you to say that this is not true. And so far, I haven't really gotten too much competition. The interesting thing is that if you want to go far out, it's very difficult to refute this, because anything outside of the Earth's atmosphere pretty much depends on optics. Even if it's particles, you could actually, make that observation. And anything out of the heliosphere is basically electromagnetic optics. We wouldn't know a whole lot about it otherwise, except possibly for neutrinos from supernovae, and that would be kind of a relatively recent thing, But on the other hand, it is hard to compete with some other techniques if you want to look at atoms. Optics can't show us atoms yet, and there are techniques that can show us things as small as atoms. And so that might be a little bit of a problem. But anyway, I'll just leave that open for you. Now, what does optics show us? Well, it shows us the universe. But most of the universe we can't see, apparently, because it's dark matter, and that, at least, we haven't figured out a way to see using optics yet. We can only see that with gravity. What optics shows us is something that we could maybe call bright matter. But the interesting thing about bright matter is a lot of people don't realize how difficult bright matter makes it to see the minority of the universe that's left. In particular, bright matter shows us the surface of stars, and we can see basically about 1/1000th of that star. The rest we can't see because it's obscured by the stuff that makes up the stellar photosphere. Okay, and so bright matter basically does just tremendous damage to our ability to see some of the most important things in the universe, namely stars that actually produce electromagnetic radiation. Okay, this is kind of a spectrum of that shows the range of frequencies of waves that we use for various purposes, not just electromagnetic, but most of this is electromagnetic, but then there are a few other kinds of waves, namely there are sound waves down here. What we see in visible light, the stuff that's familiar, is just this very small part of the spectrum. In here, it's not quite the size of a dime. Okay, the spectrum that we actually use, plotted on a log scale, is tremendous. Now you can go either way, up to X-rays, gamma rays, and so on, and see various things, but you can't see through the sun. You can't see in the solar interior. And in fact, these are even worse than visible light. You can't even see outside of the Earth's atmosphere in these. Likewise, if you actually go to longer wavelengths, things get more opaque. The further down here you go, the further up in the solar atmosphere it looks. Then around here, you get to what you could call hopelessly low frequencies. These don't even travel through the interplanetary medium. The plasma frequency around, in the interplanetary medium where the Earth is about equal to, a few tens of, or hundreds of, well, it's right about here, maybe a few hundred kilohertz. And then those waves don't even travel. You just can't see anything. You can't even see to anywhere near the sun here. But we do find that the sun has sound waves that travel in it in the solar interior, and those that we can see are way down here at about the frequency of surf, ocean waves. Okay, and so this is where helioseismology is done, where spectrally. Well, I won't go into the techniques that people do this, but in order to detect sound waves in the sun, you basically have to see motion of the solar surface. And those techniques were developed by people like Robert Layton in the 1970s, Bob Noyes, George Simon, even Jack Evans and Michard, whose name suddenly just, I can't remember suddenly, Evans and Michard and Servagin. And this is what these techniques show us. When we actually make a Doppler map of the sun, this is what it looks like. First, you can see that this is red shifted here, blue shifted here, so this kind of gradient is caused by solar rotation. The whole sun is rotating like this, and then these active regions are moving across it. The active regions I'll talk about a little bit more in a second. If you actually take out the solar rotation so that you can see some of the finer details, then you see two things. If you average over some time, you see a pattern of horizontal flows that have a signature that looks like this. Okay, the active regions have outflows from them. This is called the Ebershed effect. You don't see horizontal flows near the disk center because the line of sight is perpendicular to them. You see them away from disk center. So you see that, and then you see, in addition, superimposed upon that, you see something that looks like this. Now that's sped up by a factor of several hundred because that was about a 2-hour period there. So I apologize for showing it at way too high a speed. But you see this phenomenon that's known as solar oscillations. If you were standing on one of these, some place on the solar surface, you would feel yourself being oscillated up and down kind of randomly with a period of about 5 minutes and with an amplitude of about 20 kilometers. Okay, this would be a surfer's dream, you know. Now, it has to be realized that the actual density of this medium is only a few hundred thousandths of the density of the air in this room. So if you actually tried to do that, you would fall for a while. The place where in the solar interior where your density was something like the density of the gas would be maybe about halfway into the solar radius. It would be about a half solar radius is where the density is 1 gram per cubic centimeter, the density of water. And that's the best place to set it. Well, there, the amplitude of solar oscillations is barely a micron. So, yeah, it's microns. It's plural, but it's not very, it would be not the surfer's paradise that you would think. The spectrum of these oscillations looks a little like this. You just look at a pixel and see what the spectrum is. 3 millihertz, that's about a period of not quite 5 minutes. 3.3 millihertz, I think, is 5 minutes, where the spectrum peaks out. And this it was recognized by Noyes, Layton, and Simon very quickly to be waves in the outer solar atmosphere. And those waves have a fair amount of acoustic flux. The flux, in fact, carried by these waves, traveling through the solar interior, coming up to the surface, making a signature, reflecting, and so on. The actual acoustic flux is about a kilowatt per square meter, and that happens to be very close to the solar radiative flux at Earth. Okay, in other words, it's about a 40,000th of the actual radiative flux at the solar surface is about 40,000 times the acoustic flux at the solar surface. But since the Earth is 200 radii out and 200 squared is 40,000, then the acoustic flux at the solar surface is about equal to the radiative flux at the Earth. Kind of why that would be true, I have no idea. But so what's very curious is what is the driving mechanism? Why are these waves there? In 1970, Roger Ulrich published a groundbreaking paper about what you can do with these waves, about what their implication is as far as structure of the solar interior. And he suggested this mechanism here, something called overstable oscillations. I'm not going to try to describe this in any detail. I'm just going to try to describe it kind of graphically here. The way overstable oscillations work is if I come over here and push this guy here, all right, and now he's going to push me back. Now, it seems to me that Tommy pushed me a little bit harder than I pushed him, and if I do the same thing to him, and then he does this to me, and then I do it, and if this basically keeps up until certain nonlinear effects supervene.
We don't want any.
And that's basically the way overstable oscillations work. This depends on Tommy here having a certain amount of free energy, so that he can actually, use some of that free energy to add to the energy the work that I did on him when he pushed. And that the basis of that free energy is convective instability, a strong temperature gradient in the solar interior. And that strong temperature gradient also, we know, drives convection in the solar envelope. That's right. I think I put these out of order. That you're familiar with, but nevertheless, I love these movies. I'm going to show this. This is sped up. This is how convection looks operating for about an hour. Again, this particular movie shows it in only a few seconds, and that we're sure is driven by overstable oscillations. Well, without getting into the into the fine details, I'm just going to say that a strong consensus has developed over the years that the solar that convection is driven by convective instability, and that the solar oscillations are in turn driven by convection, not so much by convective instability. I don't know whether that's actually settled or not, but I would say that there is certainly strong evidence that that's true for most of the solar oscillations. Now, I don't really think I quite have time to go into a lot of detail on this, but probably the persons who was perhaps most pioneering and influential in this study was somebody named Lighthill, 1952. He was interested in jet engines, why they make so much noise, and he essentially then, developed the theory of noise caused by turbulence, and found that because of certain considerations that may or may not necessarily absolutely apply to the solar environment, but nevertheless that this was a very strong function of the Mach number of the turbulence. In his case, that is in the environments that he prescribed, it would go to as the 8th power of the Mach number, and therefore, if you suppose that this is the case in the sun, then you look for the places where the turbulent velocities are the highest, and suppose that those are where the sound is, the noise is going to come from. And various people, for example, simulations by people like Bob Stein, have shown that the place where the convective velocities are highest is basically in the intergranular lanes, or around the interface between the granules and the intergranular lanes. That's where you would look for these high turbulent velocities, that is where you would look for these sources of noise. And so people have done this. I think the best work is Phil Goody et al. His colleagues include Louis Strauss, Thomas Remily, and they did some great work on this, some extremely painstaking work. I actually haven't been able to stick it into this presentation here because I can't seem to get the images out of their paper for technical reasons. But they, for example, found that they could see instances of what they call sun quakes, that is, waves radiating out of certain points in movies of the granulation. What I actually showed you was intensity movies. They were looking at Doppler movies made at Sac Peak. And then they noticed when they saw these events a relationship between Doppler downflows that were preceded by sudden darkening of the intergranular lanes. And this was, very interesting. Oh, that was about around the turn of the century, around 2000 something, or maybe 1990 something, in the late 90s, I think. So what we wanted to do then, what Alina thought would be a good idea would be to apply this diagnostic that she actually helped develop for looking at sun quakes emitted by flares. And the actual technique was designed to look into the solar interior. The idea, we call it computational seismic holography. The idea would be that if you had a source beneath the solar surface and it was emitting waves, those waves would come up to the solar surface and then spread out, cause ripples that spread out on the surface of the sun that you can see. And the technique then is the computational version of applying those ripples to a model of the solar interior in time reverse. And then the model just propagates the waves right back into the solar interior. Now, the model doesn't know any better to have an absorber where the source was, so the waves just go right back through the source density, the source position, and keep going. And then you can just do various tricks. You can sample the model along any surface and get a signature. And if the surface, we call it the focal surface or the focal plane in the plane parallel representation, is near the depth of the source, you get a strong compact signature. If it's somewhere else, you get a diffuse signature. And so as you move the focal plane through the solar interior, things become fuzzy. But then if you find another source, or in this case it's actually an absorber, it works for absorbers as well, then it becomes sharp. And you can do, in principle, defocus diagnostics on what's in the solar interior. Well, our efforts to do this have basically shown us only evidence of stuff at the surface. We don't see any evidence of anything detectable, any helioseismic interaction below about 4,000 or 5,000 kilometers. Okay, it seems, at least according to our diagnostics, that there just isn't anything beneath a few thousand kilometers that interacts with acoustic waves in a way that causes a strong enough helioseismic signature that we would discriminate it from stuff that's just happening at the surface. Now, there are other people who think that there are such signatures and that they can be seen, and so there's some very interesting discussion about that. But nevertheless, we can clearly see helioseismic signatures of anomalies, active regions, and so on that are right at the surface. And our diagnostics of those depend a lot on the fact that anything that's emitted at the surface generally penetrates some distance into the solar interior and then is refracted back to the surface some distance away. And so we can do diagnostics that are focused on the surface based on waves that are that come up in a region surround what we call a pupil, surrounding the active region. And for example, some of the work that Alina Donia developed as a graduate student applied this to flares. Flares emit these sun quakes. It's a pattern of waves that come out of certain compact regions, and then her application actually refocused those flares to produce source maps that look like this. And she would find that a very interesting thing was that the sources that cause acoustic emission from flares are very compact. They're the most compact sources, and they're the most episodic sources known. And this has been very useful as a helioseismic diagnostic as well. In other words, we can look at that and say, well, the helioseismic diagnostic at least has this resolution. So it turns out that this resolution is marginally good enough to discriminate various parts of the solar granulation. Okay, the size of these splotches actually gives you a pretty good idea of what the resolution is. And this is the solar granulation here. It's about something like about 2.5 kilometers. And the solar granulation, well, the solar granulation is not even that large. So just by comparing a source density map like this, obtained by using seismic holography, with this, you're not really going to get a whole lot that's definitive, because there's just not enough statistics sitting right here, But in a day, in an area about the size of this wall here, there are like tens of millions of granules, and so you can get a tremendous amount of statistics from that, and those statistics can tell us a lot about the location of seismic sources. So what do they tell you? Well, if we look at those statistics over several million granules and compare the acoustic power, let's say, or the source density in these maps with the corresponding intensity, separate them into bins, then you get, you get this result. But before I tell you that, let's go into this. If you actually look at the distribution of those intensities, it looks kind of like this. It doesn't look quite Gaussian, and the reason it looks like this actually is because something is not quite right. You see, these are HMI observations, which is what we use to get the acoustics. But the HMI observations themselves don't resolve the granulation very well. Okay, so I'm just going to say that right now and come back to it in a little bit. Oh, it's about a half arc second. And yeah. And so that's a good question, Martin, and we'll come back to that for sure. Okay, so that's the distribution of intensities that you see in HMI images of the granulation. Okay, and where you have a lot of statistics, up around here, the meaning of a curve like this is statistically significant. The error bars are manageable. Then as you go out to where the statistics are fewer, the error bars start to get too big. Okay, but what do you find? Do you actually find something that the following, and that is, you find that in the region where the granules are just a little bit less than average intensity is where you get the most acoustic power. After correcting for certain effects, it appears that there's about 2.5 times as much acoustic power coming from regions whose brightness is 1 to 5% less than the normal than than the region where the brightness is 1 to 4% greater than the normal. And so that's good. It actually somehow reinforces the Lighthill m to the 8th rule. That's where you see, these simulations show these rapidly transonic downflowing plumes. And so that makes a certain kind of sense. But now this, when Alina was doing it, when Alina was doing this we didn't exactly expect. Okay, we just didn't know enough to expect it. What is going on there? It seems to be statistically significant, but we just don't understand it. Now, if you actually look at rather than at the mean acoustic power, if you actually multiply this distribution by this one, you'll actually get the distribution in acoustic power, and it looks a little bit like this, Kilimanjaro here, and then Kilimanjaro has a little partner. Isn't that right, Matthias? Do you know about? Okay, just checking. Yeah, or Rebecca, is that something? Okay. Oh, I'm surprised. I'm shocked. Yeah, you get something that's significant. This would be definitely. This is something right here, and so we actually then divide these up into regions: Region 1, Region 2, Region 3. Now we don't understand this. We don't, we don't exactly pretend to understand it, but nevertheless, let's consider. Now, let me ask a question here. How much time do we have?
An hour.
Okay, good. Okay, just thought I would check on that. So, I don't want to take the whole hour. I want time for questions. So one possibility is that there are just different kinds of granules. This is coming from a different kind of granule than this. So that's a hypothesis we have, and it's undeveloped so far. Another hypothesis to be considered is what we call, at least for the moment, the hypothesis of uniform granularity, meaning that all granules are the same, even big ones and little ones, and basically the acoustic emissivity is statistically just dependent on the brightness of whatever the granule is, where it is, however big it is, and then it depends on that brightness, and then on other things that are totally random, and so this is basically then how uniform granularity would statistically prescribe as the stuff where most of the acoustic power is coming from is stuff that looks like, is this. And the stuff that the second peak is coming from, that actually looks like this. It actually is inside the granule from this. You see little donut holes in, most of these. It doesn't extend all the way to the center of the granule, but nevertheless, it's still on the edge. And then you have this, the green stuff is the kind of the acoustically lazy stuff in between the red and the brown. Okay, and so that's what that would prescribe. What does that mean? Mark pointed out some interesting things, and likewise, Bob Stein, pointed this out too. Mark Rast suggested way back, almost 20 years ago. 1997, it was 15 years ago. He suggested that rapid radiative cooling was also a significant contributor to seismic emission. And Bob Stein, likewise, recently suggested or pointed out that these regions where the HMI observations show kind of an intermediate intensity are misleading, because here's what the granulation looks like if you really resolve it. And when you really resolve the granulation, you find that the brightest part of the granule is not the center of the granule. It's actually edgeward. But you see, the HMI observations don't resolve that. So the hypothetical proposition to consider is that the real granule looks like this. The HMI smearing it looks something like this, so that this relatively bright part of the granule then is recognized in our statistics as something of rather intermediate brightness. Okay? And why is that important? Because the brightest part of the granule is the part that's cooling the fastest. So this is, something that now has gone from being a total mystery, this feature here, to a very interesting proposition. And I shouldn't have even opened my mouth before we actually do the control work that you need to do this. It's fairly, it's moderately straightforward. We don't have nearly the statistics of high-resolution granular observations that we do, but we do have Bob Stein's simulations to do this on, and we also do have Hinode observations, and with Hinode observations that are co-spatial with HMI observations, we can actually look at how this assignment of intensities, this recognition would work. And so that's on our list. And so we ought to be able to report on that soon. So then, let me just summarize. There's a strong association between the sources of seismic emission, the quiet sun, and the structure of the solar granulation. That seems clear. Those plots, this should have basically been flat to within error bars if that were not the case. And so that certainly reinforces something that already is a strong consensus, and there's abundant other evidence of it, but the reinforcement is quite strong. Most of the seismic emission from the granulation emanates from the edges of granules about halfway between the center of the granule and the intergranular lanes. Now this depends a little bit on the uniform granularity hypothesis, which almost for sure is not very accurate, but nevertheless it might tell us, it might give us some accurate conclusions about certain things. And in this case, I would say that this is getting to be a pretty strong conclusion. Seems to be consistent with emission by the light hill mechanism, that is kinetic emission due to rapidly downflowing plumes that in convective turbulence. Third thing, a significant contribution to seismic emission appears to emanate from significantly inside of this region. When an account is made, kind of an eyeball tentative account at the moment is made of smearing by the HMI, these regions appear to be possibly those of greatest continuum intensity, that is, those of the most rapid cooling. This reinforces Mark Rast's hypothesis that implosive cooling is a significant contributor to P modes, even though it doesn't seem to be absolutely the major contributor. And then, well, as I say, these developments are highly preliminary. We really haven't done the control work, and so that's just where we happen to be right now. So, are there any of these? Oh, from Hinode.
No, from IMAX, from the first flight in 2009 in sunlight. So they probably have about half-hour time series. I'm not sure much longer than that.
Oh, yeah.
But the high resolution of Hinode.
Right. Well, these statistics that I just showed you are 24 hours, and they cover a fairly large, no, not the full disk, but they cover, a large enough fraction that, you see, if you start going over, then you get certain, then you start to get certain effects. Like, for example, a line of sight Doppler velocity now has a horizontal component, and that would need to be separated. But basically, I think that you probably need much more statistics than you can get in a half hour. But I do feel.
They have several maps, they're just not continuous.
And they don't have to be continuous. That at least is true. Almost all of these, pretty much all of this stuff comes from radiation that, went into the solar interior, came out in a pupil about this size here, and it took about a half hour for it to make that trip. So it ought to be, well, the problem is, though, that a half hour is
very limited.
A little long. Yeah, that's right. You really need time for the acoustic radiation to go down and come back up. So you need at least hours. But if you could get, hours in succession and put them together, then yeah, you can do that. Right. It's a good point. Yeah.
Does acoustic holography have skill at diagnosing horizontally propagating waves at the surface, or do they need to have an inward projection?
Right. There are horizontally propagating waves, what do they call the F mode. And we don't have a diagnostic for that. Now, one of the reasons maybe that we haven't paid a lot of attention to the possibility is because, if they stay at the surface, you can see them at the surface. So if the idea is that you're, trying to look at something that's in the solar interior, then that diagnostic wouldn't work.
Right.
But I could imagine, Joe, some good applications. And there is Tom Duvall at Stanford, or at NASA Goddard, has actually done some diagnostics of that kind, statistics, correlating F mode amplitudes between points, that are different distances, and looking at how those correlations correspond to things like the granulation, magnetic regions, even active regions, and is there a holographic analogy to that? There could be developed one.
You end up looking at the surface because that's where your signal is, and you have a gap in the center of the granules where the flow is probably horizontal. So that's why I was wondering if, as you move in towards the center of the granule, you get no signal, if it's part of that story.
Yeah, we should talk about that. I haven't thought about it. In the center of the granule, my understanding is that the flow is vertical, just by symmetry maybe, but that understanding may be wrong. Yeah, and that
it's got to turn over and go down.
Right, and that the highest velocity actually may be where it's brightest.
The highest horizontal velocity.
Yeah, the highest horizontal velocity might be.
You could sort that out with Bob's and with Stein's simulations.
Right, it has to be, and that's right. Bob Stein's simulations would be a really great resource, to look into that. That actually is what Alina intends to do. Yeah. I have a feeling that these do excite the F mode, for example, and that you can do some very interesting stuff with it. Martin.
So maybe this is related to what Jim was asking. But so do you attempt to model other effects besides emission? You or Mark or whoever is doing this these days? Like the
Right.
changes in the sound speed and other...
Yeah, of course we do actually, like, for example, things like looking at active regions.
No, I'm just in the quiet side, like the effects of granules on the propagation of the modes.
Right, yeah. For example, can you see evidence of the supergranulation using?
Just the effect of the granulation. I'm thinking of this, for instance, of this effect described by Boldner and Scoe, where they talk about the asymmetry in the upward and downward propagation.
Yes, okay.
That has to do. The ingredient of that is that there's an asymmetry in the amplitude, I think, of the waves going up versus the ones going down, and so in some sense the wave pattern gets corrugated by these granules, and I'm wondering if that might have any effect.
Right. Good question. You know, it seems to me that one thing that you can do, for example, with helioseismic diagnostics is essentially look at waves that are going into the sun and then coming up into the focal region, rather than what this is looking at, which is waves that are coming out. And now there's a whole series of diagnostics that we haven't developed that could very well be based on that. You know, that ask questions like, how does the helioseismic signature in a granule, how is that different from the helioseismic signature somewhere else? And
well, I was mostly thinking about the theoretical modeling.
Yeah.
For this.
Right. It's a good question. That's a good question, Martin. Yeah, don't know the answer to it. Yes, Travis.
So if I understand correctly, you're saying that most of the acoustic energy that's driving the global oscillations is coming from these downflows, these dark downflows, but that there's a second component that's brighter than average that also contributes some, right?
Sort of, yeah. Yeah, this is what Goody and Remley and those people found, but we're actually finding that it's coming in more from the edge, and that could be a matter of discrimination. Maybe we have better discrimination than they do, or maybe, you know, whatever. I mean, I do think that they definitely, their work was definitely a real result, you know. But yes, then this other region of emission is coming from something that's even, you know, that's significantly brighter than the mean intensity, you know, right at that interface that's some distance inside, according to the uniform granularity model.
Okay, so my question is there any evidence that the characteristic timescale of the variability of those two sources is different in any way?
Yes, there is, and there is a way to look into that. The correlations that we show are concurrent, and Mark Rast had the idea of putting a time lag between those and seeing what the time evolution is, and those and this is a good question. You and Mark think a lot alike, and that is, this plot then could very well change. You know, how do these decay with different time lags? Do they decay at different rates? And so that's a great.
So the reason I ask is that there's evidence in some stars from Kepler observations of two distinct timescales of like a Harvey-like background, granulation background, right?
Mm-hmm.
So in some of the targets, you can actually see two distinct timescales of variability, and the original suggestion is that one is a sort of a supergranular timescale, and that the other they attribute to faculae or something like faculae, which are brighter than granules, right?
Yes, I'm with you. Right.
So I don't know, that might be another piece of evidence that help you untangle this picture.
You know, we're certainly going to do the one thing that Mark Rast suggested. Now, as far as, say, applying this to something like faculae, there might be that's possibly a bigger job getting the statistics from faculae. I mean, you can get this kind of statistics in 24 hours because there's just so much quiet sun, you know, especially at solar minimum. But yeah, I guess really this, some of it ought to be extended. We actually have, Alina and I have looked at some of these correlations, how are these correlated with magnetic fields in the quiet sun? We don't see any correlation at all so far. So.
I don't think it's necessarily important that they. I mean, I think the only reason they identified the second timescale with faculae is because it had a different timescale, and faculae are known to have a different timescale than granulation.
Yeah, there are things like that, and to just do it on the granulation alone would give you a way outside of, would actually control that aspect of the relationship that shows these two different timescales. Right. Mike.
So from what I could tell from one of your slide titles, it looked like you were just looking in the frequency range of 5.5 to 6.5 millihertz.
Oh my God, I cheated like mad by not explaining that, because this, yeah, you're right, Mike, and I'm glad you said this, because there is a reason for that. So where's that spectrum? Oh. Yeah. All of this was done not here, but 3, 4, 5 here, where there's like only about 1/10 of the spectral power. Why is that? Well, because we know that the sun's surface is a high quality specular reflector, where these waves, in this part of the spectrum, that's very likely the reason the 5-minute oscillations are so strong, because they go down beneath the solar surface, they get created, they go down beneath, they come up and reflect, and rather than get absorbed, they go down again, and they just accumulate for a long time, okay? Now that means that when you apply a diagnostic like this, then very likely what you're seeing at the focus is something not that got produced there, but something that came in and just simply reflected from it. And so we're going out to 5 millihertz, where the amount of acoustic power is a lot less, not necessarily because the rate that is being produced is less, but because we know that stuff gets absorbed, pretty much completely in a single encounter with the solar surface. So all of this stuff that I have told you actually is not necessarily true. At 5 minutes, it is possible that turbulence produces 5-minute oscillations differently from the way it produces, 3-minute oscillations. It's a good question.
Having said that, there are no sort of distinct features in the spectrum that you were just showing us that would indicate some kind of different sources.
Yeah. In fact, around 5 or 6 millihertz, the real homework would be the control work, and it's on our list, is to actually do this at 5 millihertz, and then see if this curve flattens out. Now, at 5 millihertz, the diffraction limit is coarser. In area, it's almost, it's probably 3 times coarser, and so the statistics are going to be quite a bit poorer, just for that reason. Then it's also possible that there are other, things that would cause some correlations that we don't anticipate. Maybe some of the things that Martin was thinking about. So,
might also be able to push to higher frequencies as well.
And then, yes.
I know the power drops off.
That's right. And we actually already know that at higher frequencies, like that at 8 millihertz, we just don't see anything. For example, we can't see an active region at 8 millihertz. So for, reasons that may have to do with just all sorts of things. Martin?
All the stuff you've been showing us is with actual data, right?
You mean the sun, or as opposed to simulations?
Yeah.
Yeah.
Okay.
Yeah,
So,
HMI data.
So is there something going on with simulated data? Have you done any, like Bob or?
Yeah, we actually have about 11 hours of simulations, at NWRA that Bob Stein has given us,
Okay.
and
It's on your list.
Alita is going to, take that apart. Right.
Any other questions? Well, thank you very much again.